So, good morning, everyone. I'm actually, to some extent, surprised to see you here. It's Saturday morning. Most likely you didn't party all night. Yeah, but the topic should be actually interesting enough, I hope, for you. It is a culmination of our mini marathon. But before that, let me acknowledge again some people. So this time I would like to acknowledge Mola Maref, the CEO of Relational AI, for discussions on the motivation of this angle on the work. But also, here I will report on works done with Hung Ngo, with Mahmoud Abokamis, with Maximilian Schleich, with Long Nguyen, and Bas van Geffen, who is not here. Forgot to put him, but I will remedy this afterwards. So recall that the goal of this mini lecture series was to introduce a principal approach to in-database computation. And so far we looked at joints, we looked at aggregates, yeah? And now the culmination is to see how this work can also be relevant for machine learning, yeah? For optimization problems in general. So there has been some work done in this space, and there is much more to come. In my opinion, this is a very exciting field of research. This is why I address it to you, researchers. And in particular, you will see how concepts developed mainly in the area of databases or inherited from other areas into databases can be applicable to optimization. And I will look in particular at, first of all, motivating this and showing you the state of the art and how we can go beyond state of the art in how we can train a simple regression model. Then I will show you a different way of approaching this that takes advantage of aggregates over joints. Then I will also show another way of taking advantage of database theory. Here, I mean, in particular, looking at constraints, functional dependencies. How can we take advantage of functional dependencies for speeding up training of a linear regression model? And then I hope I will have the time to give you a very short glimpse at what I called in-database linear algebra, where the idea is that we work with matrices which are defined by queries over databases. But we don't want to materialize these matrices because they may be very large. But nevertheless, we want to do operations on them, such as QR decomposition, right? Factorization, matrix factorization overall, or low-rank decompositions. Yeah? So it's a bit interesting, thinking that you are given the input, but in a rather symbolic way, it's not fully materialized, and you like to decompose it. And you can do that in a time which may, with a complexity which may be even better than materializing that matrix. Good, and at the end, a quiz, and I have references with links. So let me give you a bit of the context. I mean, more or less, you are aware of the big explosion these days we see in techniques developed for AI, for machine learning. This is considered to be the next big opportunity. You look around and you see industries catching up on this, and I'm not talking only about the usual culprits like retail or advertising. Now you see, various aspects of society being influenced by AI. And everybody would like to use data to build models to predict things, right? Predict user behavior, predict consumption, predict other things. So this is why, a large focus has been on this ability to predict, because this is considered the core ability of intelligence. And the quality of this prediction has started to improve dramatically, given obviously, first of all, the availability of data, of training data, but also because the cost per prediction is decreasing. Yeah? And with the topic of today, we are in the business of decreasing even further this cost for prediction. And once we can do that, then we can use it obviously to solve existing problems, but solve them faster or solve them with more data, such as forecasting consumer demand, and this is quite common in retail. Or we could use it for new problems that where we did not use them before, such as instead in advertising, instead of broadcasting information such as, we sell, I don't know, shoes, yeah? Then you get personalized advertisement where you get, we sell this specific type of shoes because we believe you might be interested more in that type of shoes in that time of the year. Yeah? But there is even another trend, which is instead of a customer shopping and then getting the items delivered to them, shipped, now there is a trend to have ship then shop. That is, companies may predict that at some point in time you might need certain products, and they will already ship them to you with the caveat that you might not need them, but their accuracy of the prediction models tend to be so good that more or less you might want those products anyway, right? So, or if you don't want all of them, in any case, it's not such a big deal for them. They already, were able to plan ahead, and that optimization for them means, in fact, more revenue. So, however, if we look back and try to see, okay, but what about the data? Where does the data reside? And is this unstructured? Is this relational? And there is a survey done by Kaggle of about 16,000 machine learning practitioners. Yeah? People actually involved in using machine learning models, right? Think of them as data scientists, okay? And they were asked, okay, what kind of data do you actually use in your enterprise? And they realized that by far the most volume is taken by relational data, yeah? So it makes sense to think that we should be able to develop efficient techniques to learn models over relational data. And in particular, if we look at certain industries like retail, insurance, marketing, and finance, we see that the proportion of data they use being relational is actually pretty high. In case of retail, is 86%. And this makes sense because these people want the data, their data in retail business, to be very curated, to be very structured, to be clean, right? They invest a lot of time in this. They invest time in, adding value to the data, adding semantic information to the data, because this is the way they can actually bridge from the data to knowledge. Yeah? In other areas where, for instance, you look on Facebook and so on, right, or Google searches, data tend to be perhaps less structured, but nevertheless, there are so many information extraction tools that do exactly this. Extract structured data from unstructured data. So even when we look at text data there, it's still the case that a lot of this data may actually first be subject to a pre-process step whereby we translate it into structured data before we actually process it. Yeah? So that is a very interesting takeaway, that relational data is still out there. Yeah? As part of text data, you may also have semi-structured data, such as, for instance, these days is more, hype, to have JSON. In the time of my PhD, back, I started 18 years ago, it was more XML called, right? Here we call it also tree-structured data. And people in this department actually worked a lot on data trees and doing various, interesting problems on data trace, which is in fact as if we would work on XML, yeah? Or now, if you like, JSON. It has a different syntax, but the idea is the same. Good, so, but this is not by accident that people use relational data, right? This is actually the jewel in the database crown. There has been so much effort in the last 40 years on the relational model. The relational model was proposed in 69, roughly, right, by Ted Codd. And, so that was a long time ago. Actually, if I think it's 50, yeah, years, almost, yeah. And the relational database management systems have represented big business. In a way, they are a bit jealous now of this uprise in interest in machine learning, and they don't want to feel redundant in a way, and they, as we will see, try to bridge to AI, to machine learning, in certain ways, but rather superficial. And I will come back to that. So we have, as I said, in the retail business, for instance, but this is also in other industries, many human hours are invested in building relational models. And here on the right, you see actually a snapshot of some relational data. With the little things would be tables with their attributes. And they are, in fact, rich with knowledge of the underlying domains. This means that they are not only generated, like, in case of transactions, you get them inserted in a table every time someone pays in the shop, but you also have database analysts, administrators adding, various columns, various types, various constraints to the data. And in fact, we could go further and even claim that the availability of curated data made it possible to learn from the past to predict the future for both humans, and here I mean business intelligence, and machines, and here we really mean AI. But what is the current state of affairs? As I promised, that I will tell you how database vendors approach the problem of offering support for machine learning in the database space. The current state of affairs in building predictive models is this. You take all the structured data from the left and you translate it into a large design matrix on the right. You strip away everything, all the semantic information you have, information about keys, functional dependencies, information about how this data was put together via the joints, right? How this, design matrix was put together. What you see is this big design matrix, which is a table, in fact, with very many samples and features. Yeah? And that's it. This is actually a bit depressing for a database researcher because, database researchers do a lot of work in the left space here where they add structure, they exploit structure. The kind of main theme, right, of our course so far was the realization that if we exploit the structure from the join query that puts together these tables into a bigger table, right, you can actually be smarter about how you can compute the query, how you can represent it, and you can do it way faster than materializing the query result, right? But this doesn't happen here. What happens here is that you get these big design matrices. In most cases, they are stored in a file, in a comma-separated value file on disk, and then they are fed to systems like R, like TensorFlow, Python, scikit, or Python stats models, or you name it, right? Or SAS, or yeah. So this is what's happening, and it is actually perhaps of no surprise that these tools were not designed in mind with scalability. So how can we approach scalability in the sense of actually being able to train models over very large data sets? Well, this is still a black art for the data scientist. The way it is usually approached is you start splitting your data into chunks because you cannot possibly process it in a big chunk, like several gigabytes at a time. Even if you could fit it in memory, you could still, for instance, in R, we realized that there are so-called data frames only allowing a certain number of samples to be stored at any one time. So that's it. This means you cannot just ingest everything. But then, if you actually learn for different parts of the data, the trouble there is that you don't really capture correlations across features from different partitions of the data. So your model is inherently less accurate than if you would look at the whole data set. Yeah? And that is, in fact, an issue. Solutions in this space are mostly, well, let's throw in more hardware. That is, let's actually partition the data, put it on different servers, and learn smaller models on different servers, and perhaps find a way to combine these models. Yeah? So that's a very big trend, for instance, in systems these days, both database systems and distributed systems. How can you distribute the data so you can learn in a distributed fashion? But this actually entails a huge amount of energy consumption, and in fact, it is brawn before brain, if you like, right? You do it, brute force instead of actually thinking a little bit about that. I mean, as a sort of side note, people looked at, for instance, the true scalability of existing distributed systems like Spark. Spark is very popular these days, but nevertheless, it may only make sense if you have truly extremely large data sets, which may be of the sorts of Google, Facebook, and a few other companies out there. Most other companies actually can deal with data that can be processed on one machine, because machines can tend to be powerful enough these days. Yeah? So they looked at the following. They said, okay, let's actually learn some simple models do simple processing with Spark, or with, there are some other systems, graphics, and so on and so forth. And let's actually implement our own, little program to do exactly the same task, but that will be on one machine. It should come as no surprise that, so this was done by researchers at Microsoft in California before Microsoft shut down the whole branch, but not because of this paper. So, so what they realized is that even the time to set up the system, to warm it up and then, to have the data, to start processing, is already dwarfing, in most cases, the time needed to just process locally the whole thing, to do the end-to-end processing, right? So let alone the fact that you had actually to fire up more machines, use a lot of energy, you also need to invest in these machines, right? So all I'm saying is that in this talk, I will take a more introspective look and say, can we actually do more on one machine than actually trying to scale out by using very many machines? Because a lot of things can be done on one machine. Good. So this prompted us to revisiting this learning over databases problem from first principles. So I will show you again schematically what's going on these days. We'll get a so-called feature extraction query. This is a query that, when posed against a database, will extract the relevant information you need to define your training data set. Yeah? This may be, in our case, the natural join of the tables, but you may think that you compute additional, you aggregate parts of the data, and then you add this in as well. Yeah? So, because, sometimes you get raw features that already exist in the data. Sometimes you derive features based on the data you see. Yeah? But imagine you have such a query, and you bring together all this relevant information, and the approach so far, which is depicted in red here, is to materialize this output. And this is called the design matrix. You do this usually in the database, because the relational data mostly resides in a database. And then you export it, and then you import it into your machine learning tool. Perhaps first you'll have to partition it, as I discussed, and then you give the model to the tool, and the model will learn the parameters theta of your model. Yeah? And this effectively, I call it an out-of-database approach, simply because the learning is done outside the database. Yeah? Inside the database, you only construct the training data set. And this requires, to summarize the materialization of the query result, it requires the database system to export the data and the machine learning tool to import the data in their own format, and then may also require, in case of so-called categorical features, and I'll come back to this, what they really are, require some form of encoding, a sort of translation from the categorical space, right, to discrete space to a more continuous space. So we can have numbers, so we can deal with numbers. Okay? And if you want, you can have actually, I give there links to 2 tutorials that have been presented at the main database systems conference called SIGMOD in 2017, one from a more academic perspective, the other from an industry perspective given by people at Google, on what exists out there in terms of database plus machine learning. And there should be also videos available online if you look for them, right, on YouTube. So they describe accurately what's going on out there, right? But the claim here is that these steps are very expensive and are really unnecessary, okay? So this is the picture here of what we plan to do, and this is in green, yeah, for the so-called in-database solution. And the idea is this. Let me actually take the feature extraction query, don't evaluate it yet, and enrich it with semantic information, constraint information, any kind of information we are given by the schema and by the database. And then another thing which I will dig into in the next part of the course is from the model, we may be able to reformulate the model in a way so that we expose the data-dependent computation we need to do for training the model. And this data-dependent computation will be able to capture it as a batch of aggregates that we can evaluate over the original data. So we get these aggregates, which are given to us by the model reformulation. We take the feature extraction query, which is a join and of several tables, input or derived. We take additional information like schema. We put them in a melting pot, yeah, where we do the optimizations we've seen before for functional aggregate queries. And then we fit it into a factorized query evaluation engine, which will then spit out the values for these aggregates. And they will represent sufficient statistics for us to learn various models. These aggregates, the results of these aggregates, will then be part of a fixed point computation for a gradient descent solver. And I will describe very briefly what is this gradient descent, right, approach. Yeah? And that's about it. We use this input, which are given by our aggregates. We then, do some fixed point computation for the convergence of the model parameters using gradient descent. And after that, we compute our theta parameter. And here, the green part, the in-database part, really takes advantage of the query structure in the sense we discussed in the previous two sessions of the database schema. So we know, for instance, whether we have keys or not, yeah? And additional constraints. For instance, cardinalities and so on and so forth. Good. So to give you an impression about the amount of aggregates you'd have to compute, here are actually some tasks, right? Typical machine learning tasks that we actually looked at very recently. For linear regression, for instance, if we'd have n features, and this means also n parameters, yeah, we would need to compute a square number of aggregates, so n square aggregates. So imagine that n would be the number of columns in my design matrix, yeah? So that would be, it could be, for our retailer data set, something in the order of 40. So it's 40 to the power of 2, yeah? 1,600 roughly, right? Okay, so that's the amount of aggregates you have to compute. But if you want to go to higher degrees, like polynomial regression, where you look at, you have still a linear model in the parameters, right? But each parameter would correspond to various interactions between the features of higher degrees, yeah? Degree up to D. Or if you want factorization machines, which are a slightly more interesting model where we can also factorize the parameters. So instead of having a parameter for every interaction, you can actually have a dot product of parameters for the different interactions. And in case of classifications such as decision trees, we need that amount of aggregates to compute. So for n features, and so we have n variables in the query, but we want to construct a decision tree of k nodes, then we will have to look essentially, at the different variables. If they are continuous, let's say it's about the sales, you can construct nodes of the form, if sales is less than a certain amount or is greater than a certain amount. But in case of city, which is a categorical feature, you may want to say, is city London? If it's London, you go on one branch of the decision tree, otherwise you go on another branch of the decision tree. So you have to compute a lot of aggregates, which will tell you how frequent a certain category is in the data. in a way, right? So you have to compute a lot of aggregates. But the beauty about this is that these aggregates are quite similar, and they all have to be evaluated over the same join. In particular, I will dig more in this course on the linear regression case because it is just amenable, and I think it's easy to understand it without actually requiring a lot of hours of inspection. But then we can also do unsupervised techniques such as k-means or principal component analysis or learning structures of Bayesian nets, so-called the Chou-Liu trees, right? And they, have this corresponding number of aggregates. So these aggregates can be very many, and there is a challenge, how to compute them efficiently. But nevertheless, all of them are computed with kind of techniques I presented to you yesterday. Yeah? Right, so does this matter in practice? So let me give you a short introduction to this. I will take a retailer data set, the one we discussed also in the previous settings. Imagine we have store, inventory, weather, demographics, and items, and we have essentially 2.1 gigabytes on disk, right? So the inventory is the big, fact table with 84 million tuples and about 2 gigabytes on disk. It represents a three-dimensional tensor that takes location, date, and product identifier and maps it to the unit, the inventory units, right? How many inventory, units I have in the inventory for that particular combination, yeah? And the goal here was to train a linear regression model to predict inventory units, and the design matrix would be defined by the natural join of all these relations. We take away the join keys because these are not useful features, because there are some identifiers, right? What we realize is this: if we do the join of these tables, we get roughly about the same number of tuples as the largest relation inventory, 84 million. Then the time to compute this join in Postgres would be about 217 seconds. Then you'd have to export it, and that takes even longer, 373 seconds. And then if you like to learn the parameters of this model using TensorFlow, which is the system proposed by Google, it will be at least 12,000 seconds. So we stopped at that time. That would be the time roughly taken to do one epoch, which is let TensorFlow run over the trained data set once. But usually, in order to get good parameters, you'd have to actually perhaps go several times over the trained data set. But in this case, we just let it once because it already proves our point. And TensorFlow would use a special form of gradient descent. By default, it uses this follow the regularized leader, which is a form of stochastic gradient descent. Yeah.
Have you compared this with how XGBoost would handle it? How much time would XGBoost take to run on this site? XGBoost, right? Because the state of the art for this type of data is to run XGBoost, right? To not do neural net, just run XGBoost on it.
Well, I mean, we didn't try exhaustively all possible systems out there. We tried, I think, about 6, 7 of them. And they all exhibit time which is large. Yeah, okay. I'll give you the punchline.
This is just linear regression, right?
Yeah.
It's not. Okay, this is not neural net.
Yeah. But it can do that, right? Yeah. Yeah. So we use this. We used before, for instance, other systems out there like MATLAB R and others to see the times, but the times were actually not far from this. Okay, so what we actually did, for instance, on this column is the approach taken with TensorFlow that gives us something like 12.5 seconds, 1,000 seconds at least, right? Our approach, which is on this side, actually computes all these aggregates in 18 seconds, and the convergence step on top of these aggregates is done in half a second. Okay, if you want to learn another model over a subset of the features that we used to for the aggregates, it will take another half a second. Okay? So everything we've seen so far goes way, way beyond that. Yeah? It doesn't do it in 18 seconds. Yeah? So I guess the question is really, mute. Yeah. All approaches that actually have to rely on first computing, materializing the design matrix, they are already lost in this setting, okay? And all of them do. So that is about at least 600 times faster, and we looked at root mean square error of the model computed, and that was about 600 times better for us. So we took away a test data set and we basically compared that, right? So that is just to motivate for you a bit that this is actually interesting. I don't want to go into details of various systems and so on and so forth, but that is just to serve motivation purposes. So let me go actually more into the technical bit. Yeah. So model reformulation. So here is a rich linear regression model. So we like to learn something like that. This is a linear function in the thetas. Thetas are our parameters. I write it here using this dot product form, which effectively means a sum of the corresponding theta with the corresponding x, right? Theta I xi plus theta, theta I plus 1 times xi plus 1, and so on and so forth. The x's are the features, the ones we get from the training data set, and the thetas are the parameters we want to learn. Here, I actually still leave it in this form. I assume that f, the big F, would represent to us the set of free variables in the query that defines the training data set, okay? So we have this database I, we have the query Q, we apply the query over the data set, we get back a training data set D, and in D, we'll have features represented by columns, okay? And we have F of them. For instance, features there could be the city, the country, could be various demographics, and so on and so forth, okay? And I will get back to this a little later. So we also have, in the training data set, a label. So the training data set tells us not only, oh, I have these features, but it tells me also, for these features, this is the label, this is the response I see in the past, right? So we'd like effectively, in order to learn this linear function, to do exactly this, to use this objective function that has two components. One is the least square loss, one is the regularizer, and the least square loss does this, says, okay, I actually compute, so this is our function we want to learn, right? I compute for that sample in the training data set, the answer, the prediction, and I actually look at the difference, the error between what I predict and what I see in the data. This is supervised learning, right? And then that error, I square it, and then I sum these errors over all samples in my training data set, okay? And what I want is to minimize this error, right? So I want to minimize this function. I have a second component, which is the regularizer, which actually tells me that I would like to avoid some overfitting, right? So this is, in fact, the L2 norm, yeah, of my parameters theta, and I will try to minimize that as well. So that I don't actually know, I will have perhaps very many choices for the parameters, and I want to take some to take a vector of parameters where the variance is actually small. Yeah, okay? So that's the idea. And this parameter lambda, well, there is so much history on this, right, in the machine learning courses, right? It will tell me how biased I am. If I increase it, right, it will mean I would like these parameters to be very, very low. But the whole term here, in fact, is about avoiding overfitting. I mean, having a bias towards parameters that have a smaller value. Yeah? So this is the optimization problem. I want to minimize this with respect to the data I'm given. Yeah? So, but before showing how to do that, let me actually give you a brief side note on one-hot encoding of categorical variables. So we have two types of variables or features in our case, right? We have the continuous ones, and they are mapped to scalars. So in that case, we can talk about x underscore unit or sales. These are real values, yeah? Or we can have categorical variables, and they are normally mapped to indicator vectors. If you remember, we discussed about indicator vectors also yesterday a little bit, in the context of an aggregate query. An example of a categorical variable could be country. And assume country has two categories, Vietnam and England. Then country is mapped to an indicator vector of this form. X country, in this case X is bold because I want to say it's a vector, right? Is Vietnam, X Vietnam, X England, right? Transpose, it's a vector, right? And it has values in 0, 1, right? In this, 0, 1 square. So this means that either Vietnam is, X Vietnam is 0 and then England is 1, or the other way around. Okay? So for instance, X country would be 0, 1 for a tuple with country equals England. So England has position 1 and Vietnam will be 0. Obviously, if you have large domains, this may lead to a lot of zeros in the representation, but there is something more to this than just having the zeros, is that the way you normally do it is you take the design matrix and you transpose the domain, the set of categories, into the schema. That is, instead of actually having just one column with a country, you now have very many columns, one per category of a country. So one per country, essentially, right? So you'll have a column for England, a column for Vietnam, a column for Poland, for instance, right? And so on and so forth, right? And then the indicator vectors represent the values you have across these columns, right? 1, 0, 0, 0, or so would say, Vietnam, we talk about Vietnam in that sample, and 0 for the other categories for the other countries. This means we don't talk about them. Yeah? Okay? So blurring the distinction between the arity of our relation and the size of our relation can have some implications. If you remember, our setting is that where databases tend to be, tables in databases tend to be very thin and tall, right? And we explored that somehow in many ways. We exploited it, for instance, by saying that, the schema of a database is small and constant, whereas the database can be very large. And we optimize for, basically having a lower polynomial, if at all possible, in the number of samples in the trained data set or in the size of the database, and not necessarily in the arity of relations. But I will show you a way to get rid of this thing. So we'll not use a one-hot encoding for our processing, but rather we'll use queries with free variables, in fact, to avoid this situation. So how to get now from the optimization to the sumproduct queries? We like to solve this minimization problem. We like to compute the parameters theta that minimize our function j, our objective function j, and that can be done, for instance, by repeatedly updating theta in the direction of the gradient until convergence. Yeah? So in more detail, if you look in algorithm 1 in that paper, you'll see the exact way we frame this, right? It's a bit more because it uses some special interesting line search that proved to be actually better, in particular to decide on this step rate alpha. Because this effectively says this, I start with some values of the parameters. So this theta is in bold, meaning I'm talking about the vector of all parameters. And then I take away, so I move in the direction of the gradient, right? I take alpha times the gradient. Okay? And I do this several times, right? I can do this, fixed number of times, or I can do it until convergence, which means that the difference between subsequent steps on the values of theta would be so small that I can deem that this already converged. This is one approach, which is an approximation. Another one, especially for linear regression, is to compute the closed form solution, right? Which is also possible, and which could benefit similarly from this approach. In fact, we will see a bit later how we can do it via the linear algebra approach using QR decomposition. Okay? But that's the idea. The idea is that this is the convergence step, and we'd like now to understand, what is this gradient and whether we can decouple from it any sort of aggregate computation. So this idea of model reformulation is this. We look at this objective function j, we look at the gradient, its gradient, right? And then we say, can we rewrite the formula in a way so that we decouple the parameters, theta, from computations we have to do over the features and the label, x and y, in the training data set. Because if we can do this, perhaps that is just an in-database computation which we can do efficiently. Yeah? And that's the whole idea, to decouple the data independent, which is the theta, from the data dependent, which is x and y. Okay? And that's the way we can do it. This j, which is stated here, which is the original square loss function, yeah? Square loss plus the regularizer, L2 regularizer, can be written like this, right? Where sigma here would depend on the data, theta does not depend on the data, C would depend on the data, and this would be some parts which will not depend on the data. And then if you believe that this is true, and I can show you now on the board, then if you take the gradient of this with respect to theta, you will just get directly this, you know? If you take the gradient of this is sigma theta, of this is simply C, and this actually, it's just about the label, and this is theta, so we get lambda theta, okay? So how can you get that, right? So it's not a big deal, but, you know, for the purpose of making sure we are on the same page, let me just show you for the loss function how to do this, right? And then we have theta x minus y squared, okay? I simply expand this into theta x squared plus y squared minus 2y theta x, yeah? Now, this here, you could actually have it as this, is theta x times theta x, right? But this is a scalar, because, you know, effectively, this dot product doesn't mean anything else but theta transpose x, right? So theta is a vector, x is a vector. The dot product means you multiply the corresponding entries, right? And if you want to do this using a vector notation, you transpose this. So this becomes something like this, multiply with something like this, then this is multiplied with this is multiplied with that, and so on and so forth, yeah? This dot product here, you know, is symmetric, so we can turn it around. So this would be x theta. But x theta, we can also write it as x transpose theta. Okay? So ultimately, this will give us to theta transpose x, x transpose theta. Okay? Now, in this formulation, if you look close enough, this x, x transpose depends on the data. These are the features. This, you know, you get them from the samples. You go over the training data set D. Thetas, flank it. We don't need to touch them. We will need to compute this first, because this is something we are good at computing, right? You will see that this is an aggregate. You know, not only one, but a bunch of aggregates. What about this case? So y here is a scalar. This is again a dot product of two vectors. This you can easily put it into theta and 2yx. Yeah? You take this and put inside, so that here you have data-dependent computation. Theta stays away. No, you can also write it obviously as theta transpose 2yx. But then, you know, if you multiply with this guy here, 2 goes away with 2, and then y times x will go over the number of tuples in the training data set. This is a count. It's a count over the feature extraction query, which is something we can do efficiently, right? Again. And what about the rest? The rest is y squared, which is essentially the square of the label, which will be also over, you know, the count here. So now we are left with doing the following operations. If we would conceptually go sample by sample, right, in the training data set, we'd have to compute this here. which is a dot product, if you like, of x with itself, of the feature vector, right? Itself, and then we get this here, that is, we take all the features and we multiply them with the label, right? And we also have the label multiplied with itself. Okay? So this is why it should come as no surprise that we can actually take, all this, we can represent them in the following form. So for this guy here, think of it as actually, so this is not a dot product, sorry, this is a matrix because it's x transposed. So it is like, I take this would be x, and I take this is x transposed. So what I get at the end, I get a matrix like that, where this and this will go here, then with this thing will go here, and so on and so forth, right? So I take all possible combinations of the x's, right? So if x would be a vector representing, if you like, cities, country, various demographics, and so on, I take all possible combinations of them, okay? And I take them over every single sample, so I sum over the sample space. And that is exactly what happens here. So what happens here, right, is I take all possible indices xi, xj, right, and then I take them over the size of the training data set, and obviously I have to sum up over all the elements in this training data set. Is that clear? Good. So now I do the same for the interaction of every feature with the label, and I do the same, interaction of the label with itself. Okay? So you see the power of this trivial transformation. The power is that now we took away the things about parameters which will be relevant only in the convergence step from this data-dependent computation, which is xi, xj. Yeah? That, we may do it once. We look at the data once, we compute this. This is an aggregate, in fact, a bunch of aggregates. And once we computed that, we can then use it in the convergence step. Okay? So, in particular, I will show you now how you can represent this using FAQ, using functional aggregate queries, these entries. I will talk only about the entries in this sigma matrix, we call them. This sigma matrix is very much related to the covariance matrix, in fact. Yeah? But it's not quite there because the covariance matrix, for those who know, is actually centered. You have to take away from this product the mean. Yeah? But if you take the mean, it is exactly the covariance matrix. Yeah? Covariance matrix is very useful for a lot of other things, by the way, right? So being able to solve this efficiently, actually we can solve efficiently also the covariance matrix. And that is used for instance, principal component analysis, which is also something that can be done with the same principle. Yeah? And if you have that, you have the eigenvalues, you have the eigenvectors. Yeah? Good. So, yeah?
One question. When you have xi and xj, here these are the values of the particular features, right? Xi and xj correspond.
So this is a very good question. This is a very good question. I wanted to come exactly on the next slide, but I can explain it here. The idea is that I use them in bold for the following reason. If xi really corresponds to a scalar, I mean to a continuous feature, then it is a scalar. It will be then, not bold. But what happens if this is actually a categorical feature? Then this xi will be, in fact, there an entire vector, right? An indicator vector, right? So for if I would be country and j will be city, then you effectively, what you have there is a multiplication of two vectors. One for the city and one for the country of indicator vectors, right? Per sample, right? So this depends on the actual type of the feature. If the feature is continuous again, then that would be a scalar, and you do just normal multiplication of scalars, right? But if that is actually a categorical feature, you cannot really multiply London with, I don't know, Poland, right? Because it doesn't make sense. But then you can actually have indicator vectors and multiply them.
So how do you multiply it? Coordinate-wise, or what do you do?
So, I mean, if you have a vector with another vector, right, you just multiply them. Yeah, you get this matrix. You get a bang, you get, you have, I don't know how many you have here. Let's say you have n cities, and you have m countries, you get this n by m. Yeah? But the tricky thing is that a lot of these entries there will be 0 in this matrix. Because obviously London is not in Poland. Or is it? Is there a London in Poland? Londek. But does this actually really meant to be London? But no.
It was a movie reference. There is a Polish movie where there is a lady tries to buy a ticket to London, and the cashier answers her, "There is no such city as London, there is Londek."
Okay, but there is also Lodin. Is Lodin a city? No. In Poland? No. Perhaps I don't pronounce it well. Lodin? I thought that there was a book about a man in Lodin or something.
Yeah, but so like the German name for the city would be Lodin, Lodin Merch, and so on. But like Polish is Łódź.
Ah, I see. Okay, so going back to this thing, right? We have a principled way, a sound way to do it, but we like to avoid the zeros. So the way to avoid the zeros is to really think of these sigma entries in the sigma matrix as being, in fact, FAQ queries. So there are 3 main cases we should consider. One case is when both xi and xj are continuous. Another one is when one of them is continuous, the other is categorical, and yet another case is where both are categorical. Yeah? So let's start with the case where they are categorical. So this is actually at the very end here. What does it mean to be categorical? One way is exactly as also you guys, you already had the intuition, and Shimon also discussed about this. You would construct such a matrix. You take the vectors, and you basically, it's like an auto product, if you like, and you make a big matrix. But another approach is to only account for those entries in the matrix that are non-zero. Which are those entries that are non-zero? Those that appear in the training data set together, like, Warsaw and Poland, right? And not Warsaw and UK. I'm pretty sure there should not be Warsaw in the UK. Okay? So you see, so this means that conceptually the way we can do it is to have both features as being representing 3 variables in our query. So we look at possible valid combinations of the cities and countries, and for each of them we compute the frequency in the training data set. Right? We say, oh, this appeared this amount of times. This pair appears this amount of times in the training data set. I record that. So I effectively compute a count, right? And I will explain exactly what this means, right? But effectively what this does is computing a count representing the frequency of that particular combination of city and country. But I'm only looking at those combinations that do exist in the data. And by this, I actually lower the complexity of doing this operation, and I avoid all the zeros.
What do you mean that a combination appears in the data?
For instance, in the training data set, when you do the join, right, you will not have Warsaw appearing together with UK unless this is the way it appears in the input. Right?
So how do they appear in what relation? What do you mean by appearing together?
Yeah, so for instance, okay, so take for instance the way we do the training data set. We construct the training data set. We have a query which says, in our case, would join tables, right? And we have tables that describe information about cities and about countries. And between these 2 tables, city and country, there may be some key foreign key connections, right? So, so that you can recover that this city appears in that country, okay? So in the training data set, you'll have those valid occurrences, that Warsaw appears in London, that London appears in the US and in the UK, right? So you'll not have all possible combinations of the cities and the countries appearing in the training data set.
So you essentially assume you have a table which says this entity appears together with this entity, is that?
No, I don't make assumptions like that. All I'm saying is the data tells me, right, the input data tells me that I have these cities and I have these countries, And the tables already have some relationship between them because I joined them somehow. In this case, I joined them by, let's say, a key foreign key join, right? And that key foreign key join would tell me that this city appears in that country. And in particular, city implies country. There will be a functional dependency.
So the data set like stores, and in stores you have a table store to country, store to city, and if you would join them over the store ID, you would get this big file, 23 gigabyte, which says store number 1 is in the country Poland and the city Warsaw. So store number 10 is in country England. And
yeah, so that's what I mean. You essentially have a table which combines the two entities somehow, in some way. Yeah, this is what.
Yeah. So whatever is given to me in the input, right? Whatever is given to me in the input, when I actually have to account for their interactions of the features, feature city with feature country, the data will tell me that these are the valid combinations possible, right? Right? So that is, to think about the result of a join. You look in the result of the join, and you realize that country appears with the city, another country appears with another city, and so on and so forth. These are the valid combinations. The combinations are sparse in the sense that you don't get all possible combinations, all possible cities with all possible countries. Okay? If that would be the case, then our matrix will have no zero entry. Because it would mean that all countries can be combined with all the cities.
So in other words, you just take the join and you project out on the two coordinates and you see.
Yeah. Exactly. And that projection is done by such a query, right? It says, give me for every pair city country its frequency. But by design, such a query will never give you pairs city country which will not appear in the data. Because they will look exactly at the projection, as you said, right? They will not look at possible combinations which do not exist in the data. Because when you ask a query, select city, country, and the count from the data, from the join result, group by city and country, you'll not get pair city, country that have a frequency of 0. Because they will not appear in the input, right? So why should you get that? No, so SQL will never give you that. Query processing in general will not give you that. The join will not give you that, and the aggregates will always be positive, strictly positive. Yeah, and this is what we actually capture here. That we basically sum up, we aggregate away all the variables of the query, except for variable xi and xj. That can take such a pair of values ai, aj. And this product represents actually the join. I join all relations from R1 to Rk, which could be 5 relations in our training data set, right? Let's say if it is retailers. And this one underscore this is only there, it's a technicality, but I will explain nevertheless. This is at Kronecker delta. It says that this function evaluates to 1 whenever indeed I have that particular tuple, right, in the relation. Otherwise, it evaluates to 0. So I essentially here look at all possible valid assignments of the variables to values in the domain so that the join is satisfied, right? And for that case, I actually count. Now, if I have both features continuous, what I do, I take their product and sum over the values of this product. Yeah? So for every sample, right, I take xi times xj, and then I take for the next sample as well, and I sum up over all these products. Yeah? But now comes the tricky thing. What we discussed yesterday applies immediately here. We'll never evaluate an FAQ query like this. We'll never say, do the product here, construct the big thing, and then look over sample one by one, okay, and compute a product and sum up. But rather, the way we will do it, we'll take some of these sums and push them past the product using the rewriting we learned yesterday. Yeah? In particular, such a query could be evaluated in time which is proportional to the size of the database, original database, to the power of this fractional hypertree width. Yeah? And that can be one for all these kind of, acyclic queries, queries that do not have these sort of loop cycles, right? And, but nevertheless, if you look at the size of the result, yeah, if you look at the fractional edge cover number, that can be way, way larger than the fractional hypertree width, as per our discussion from the previous 2 sessions. Similarly here we have 2 free variables. So the way to evaluate this, you take a variable order where these 2 free variables sit on top of the others, and the others may branch out any way they like, right? So that you can evaluate it way faster. This for such acyclic queries where you don't have loops, you don't have loops in the hypergraph, effectively could be done in time quadratic, right? In case, city and country are not part of the same relation and there is no dependency between them, then there may be quadratically many combinations of them. But everything else can be just aggregated away, linearly, right? But if this xi, xj are part of the same table, then such query is also, evaluated linearly on top of the factorized join. So essentially with fractional hypertree width. Sorry, yeah? So what about the in-between case? We have categorical and continuous. Then the categorical feature becomes free. The other one remains to be aggregated over. Because it's continuous, it's a number, we can crunch it. Yeah? Okay? So that's the intuition for this. And now we don't get one query of this. We get very many queries like that. I tried to make a case yesterday that for some regression models, like a linear regression model, we may get in the order of some thousands, right, of aggregates to compute. But for if you go, tens of thousands, but if we go to polynomial regression degree 2, we may get something like hundreds of millions of aggregates to compute, all over the same join. But they can still be done very efficiently together. Yeah? They are quite similar, but not the same. Yeah? Okay, I mean, I will, for sake of, even better enforcing this idea, I will now explain how you can encode this in SQL. So in case...
Sorry, could you come back there? So what do you do with those psi ij's when you define them and...
you evaluate them after that.
But how do you use them? So you want to evaluate them to plug them in somewhere to compute your...
Yeah. Look here. These psi ij's represent the entries in sigma, or the entries in C. Right?
Yeah, so what is the relationship of the psi ij's with sigma?
Well, here I say we have these queries for each sigma ij, which is an entry in the sigma matrix, okay, is defined like this. So every entry in the sigma matrix is defined like that.
So the psi ij is defined sigma ij.
Yeah, it's defining this. Yeah, so it's an entry in there, right? But I didn't understand that. Yeah. Okay, sorry. So yeah, so this entries in here, right, for a particular, row and column, sigma ij would give you this thing, and then, this thing, this particular entry can be defined using one of those types of queries. Okay, and once you have that, you go back here at sigma, you have your sigma defined, and then using these equations, you go back into the convergence step. Yeah. Okay. Good. Perfect. So now I was about to show you how you can define them in SQL. In SQL, so you can use actually an existing database management system to do some of this work for you if you want. You don't need a proprietary system. Like you can use open source Postgres, for instance, right? In case xi and xj are continuous, you do this query. You select the sum of the products of xi and xj from D, but D now is our join, which we do not necessarily materialize. So there, instead of D, you basically plug in the whole, join query. Yeah. Okay. Then, in case xi is categorical, xj is continuous, then xi becomes free variable. In SQL terminology, this is a group by. Right? You group by xi. For each xi distinct value, you compute a sum over xj from the same join. And then, in case both of them are categorical, then you have both of them free, that is group by, and then you compute a count, the frequency of that occurrence of that particular combination of categories for xi and xj. Yeah? Now, obviously, you wouldn't like to issue these queries in Postgres one after the other, but rather you put them together because they are over the same D, right? There are ways to do this together. I mean, to just construct a bigger query to do everything together. And that you can optimize, rewrite the way we discussed yesterday. Good. So this query encoding is much more compact than the one-hot encoding because it doesn't really need to deal with the zeros, right, with the non-existing combinations in the data, and can sometimes be computed with a lower complexity than D even, right? And that we discussed because effectively this claim here is the claim that this particular fractional hypertree width of the query, of the feature extraction query, is actually lower than, is smaller than the fractional edge cover number, right? So that's the actual thing here. So if we try to put this together in a picture, in a more, refined picture, the one I gave you originally, then the red part is again the out-of-database approach. The green part is the in-database approach. The out-of-database approach essentially, materializes the join. Here we have the x's, the y's, and this will be of size, which is the size of the database to this fractional edge cover number. That you fit it into a machine learning tool, but maybe very large. You take the model and then you learn the parameter. Alternatively, from the database with the schema, with the feature extraction query, the model reformulation I just showed you, you get these queries, which are the entries in the sigma matrix, are the entries also in C, and so on and so forth. They all become input to the query optimizer, where we rewrite them efficiently, so we can attain our fractional hypertree width to evaluate them. Okay? And that may be actually way smaller than doing it out of database. Are there questions about this? Is it clear? Perfect. Good. Let me say a few things about the complexity, right? More precise things about the complexity. So the complexity of learning models falls back to factorized computation of aggregates over joints. In particular, if you want to compute these tensors sigma ij and cj, you can compute them in this time. So this is a more refined complexity from what I discussed before. So effectively, you look at each entry ij, yeah, and then that each of them will have actually its own width. Why? Because they may have free variables or not. Yeah, and that is the complexity of computing them. This is the output size if you want to materialize them. And for all of this, you take a logarithmic factor in the size of database for initial sorting, as we discussed, right? And there is a factor here which depends on the query, which is basically the number of relations and the square of the number of variables, of the features you have, right? So this is one thing that you don't need to show if you only talk about data complexity. I mean, you consider parameters like size of the query, number of variables to be fixed and constant, right? If they are constant under the big O notation, they go away. Good. So that's the thing. One result we actually showed 2 years ago was actually for the case where everything is continuous. When everything is continuous, so you don't have free variables in these sigma entries, right? They are all over continuous, then it's obviously easy. All these fractional hypertree widths for the specific entries will all collapse to one fractional hypertree width, which is that of the feature extraction query. Because, we will only compute queries without free variables, right? So in that case, you get this complexity, okay? So that's about it. So because I want actually to talk about the learning under functional dependencies and then have a break. So far, I presented to you the framework in which we could learn these models efficiently by this translation from the optimization problem to aggregate computation. But there is much more than databases can offer us. And I will give you an example of yet another thing that can be useful, namely functional dependencies. Because you see, if you have city and country, there is a functional dependency here. Yeah? Well, perhaps not so much in real world, but you have to bear with me for the sake of this talk. I know there are Londons and Oxfords all over the world, so I cannot make a case for city imply country, but for the sake of this talk, I just make it. So I consider this functional dependency. So what does it really mean, a functional dependency? It means that if you have a city, let's say Warsaw, then that city is situated in one country only. You cannot have that city appearing with different countries because it will not functionally determine the country anymore. Okay? So here, for the sake of an example, I take two countries. I take Vietnam and England, and I take 5 cities. I take Saigon, Hanoi, Oxford, Leeds, and Bristol. And then if we reason in terms of the one-hot encoding, the indicator vectors, then X Vietnam is in fact, X Saigon plus X Hanoi, right? So in other words, we can interpret this as X Vietnam is 1 exactly when one of the two is 1. Either Saigon, X Saigon is 1, or X Hanoi is 1. And we know that in a tuple we cannot have both. The tuple says, under the column city, it either has Saigon or Hanoi, in case the country is Vietnam. Now, for England, it's similar, but now we have Oxford, Leeds, and Bristol, and England is 1 when exactly one of those is 1. Oxford is 1, Leeds is 1, or Bristol is 1. Okay? How can you take advantage of this? So we start again with these identities that are due to the one-hot encoding, and these are fairly clear. And we would like to construct a matrix, a sort of mapping between the countries and the cities. And this matrix R, as you can see it here, okay, has on the rows the countries, on the columns the cities, and it records exactly with 1 and 0 whether a city is in a country. In particular, it says that Saigon and Hanoi are in Vietnam, and the other 3 are in England, and 0 otherwise, okay? But you can think of this matrix as being, in fact, represented by a relation, which just captures, has 2 columns, city and country, and says, oh, this city in this country, this city in this country, and so on and so forth, right? But for the sake of various derivations I will do here on the board soon, I consider a matrix. So we can do reason using linear algebra. So if the city is Saigon, then city is like the X city would be like this. It would be this indicator vector, because Saigon is first in my order. Okay? And then the country is Vietnam, because I can compute it as follows. I can take R, my matrix, mapping matrix, and I multiply it with the vector X city, and that will give me the vector X country. Because indeed, if this is R, and this is the vector, indicator vector for the city Saigon, then if I multiply this, I get 1, 0, which is an indicator vector for country, which tells me that the country must be Vietnam. Is this clear? Good. So, how can we proceed? We do 2 things. If you look at our objective function, we have 2 components. One is the square loss, the other one is the regularizer, yeah, L2 regularizer. And we like to rewrite them in a way so that we somehow throw away the parameter country and features related to country. In other words, we want to reparameterize the model, right, in a way so that we actually compute a smaller model that doesn't talk anymore about the country, and then we can map it back to the full model that also has country. Okay? Does this make sense? So now the question is, how can we possibly change this objective function to account for the fact that we took the parameter theta for country away? We took it away. How can we do that? So first of all, we look at the case of the square loss function and see how we can take it away. And the second thing will be to look at the regularizer. The regularizer is a bit more complicated because it is a quadratic function. The square loss here is actually, well, it's still quadratic, but somehow it's easier. Okay, so let's see. So this is in fact, right, the our model, and we say, oh, the model was, a dot product of the parameters theta with the features x. Let's actually isolate away those features that do not talk about city and country, and have separately those that talk about city and country. Okay? So I didn't do anything, that I took these two away from this sum. And then the second step is, I replaced, instead of the x country, I put r x city, because this is the identity we are given, right? So if we do this, then we can actually move r to the other side in the dot product and take it as a transpose, okay? And then we have r transpose theta country plus theta city in a dot product with x city, which is exactly what we have here, okay? And based on this, we can we could call this component here gamma city. So it's a new parameter. We introduce a new parameter gamma city in place of the two parameters we had before, theta country and theta city. Okay? And now our model will talk about all the other features and parameters, and now including a new parameter gamma city. Yeah? Which is now in a dot product with x city. Okay? Good. So this effectively amounts to not computing anymore aggregates over x country. In a sense, it makes sense, right? Because this x country was always determined by x city, so whatever we do with x city, we can then get also something about x country. So we reparameterize then and ignore the parameters theta country. There is not only a single one, country being a categorical feature, there is a parameter for every single country in there, right? There is a parameter for England, there is a parameter for Vietnam, and so on and so forth. So now let's look at the penalty term. In case of the penalty term, so first of all, we start with our identity, that the country is defined as a function of city using R. Then we just introduce this substitution, that gamma city is R transpose theta country plus theta city. So now let's look at the penalty term. So this was the penalty term we had, right? Okay? So this is effectively a saying, let me isolate those thetas, the norm of those thetas that are actually not talking about city. And then I have those, well, here I should have said also not city and not country, sorry. And then that part that talks about country, no, it talks about city, sorry, because you see, theta city from here is gamma city minus this term. So I could just plug it in here. And I can also have theta country. Okay? So far I didn't get rid of theta country. To get rid of it, we can basically optimize it out by expressing it in terms of gamma city. How can we do that? We take the partial derivative of our penalty term with respect to theta country, and this will give us something like this. I mean, if you look here enough, you stare enough, you realize that this is the derivative of it, okay? So why so? Because here, this is square, so we take 2 times the derivation of this times itself, right? But the derivation of this is simply minus R transpose, okay? So this minus, and if you multiply it with itself, gives us exactly this, okay? And the R transpose, if we put it to the other side, will be R here, okay? And then we have still theta country, because if we take the derivative of the theta country square, we get 2 theta country, okay? But we have a lambda over 2 here, so 2 with 2 go away, and lambda was here in front. So we just took it away as a constant, yeah? Okay, so that is our expression. We equate this, we set this to 0, and we obtain theta country in terms of gamma city, okay? So if we equate this to 0, you get exactly this. So why so? Well, we have theta country in two parts. We have essentially theta country here and there. So if we take this, will be R transposed plus identity times theta country minus gamma city. So gamma city will be on the other side, right? So I can actually write this down. Okay, so we have R transposed theta country. I would just say theta C. No, I have to say country because I have city as well. And gamma city, right, plus theta country equals 0. So this is R transposed plus identity theta country equals equals R gamma city. Yeah? And I multiply this, both sides, with the inverse of that. So if I multiply with the inverse, then this inverse times this will be identity. So then I get theta country equals R transposed plus I minus 1 R gamma city. Is this what I got there? Yes. Yes. And now the question is, what is this I? No, it is here. I talk about this first. Yeah, you can also write it in that, but let me get there. So this I, if you look at the dimensions of R, so what is R? R is defined, hold on. R is of dimension country by city, right? So if you take R transposed, country by city times city by country, you get I to be the identity matrix of dimension the number of countries by the number of countries. Okay? So this is why on the slide it is written here I of country. And you could also write it differently in the other form. Essentially, instead of looking this way, you do it with I city. But then it requires another derivation form. Okay? But they are equivalent. I just wanted to show you the first. Okay? So effectively what I did is that I was able to express theta country as a function of gamma city. I have also expressed theta city as a function of gamma city and theta country, which is exactly at the very top. So the very top here I have, as you can see, theta city can be expressed as gamma city minus this quantity, which depends on theta country, okay? And theta country is expressed in this form, depending on gamma city. So I can rewrite both of them to depend only on gamma city. Okay? So if I do this, I get, okay, so this is theta country, and then the penalty term becomes something like that, which is actually a bit of a stretch, I guess, but I can easily go over it. Well, not easily, but hopefully, it will work out. But I can definitely try to go over it. So what I have is this, right? I write again that theta country is what I just wrote there is, okay, so I can write it in terms of city, R city plus R transpose R minus 1 gamma city. And theta city is, I had it before, so let me go back to this. I had it as gamma city minus R transposed country. But I will just inline the theta country in here, okay? So this is R, this is I CT, plus R transpose R, minus 1 gamma CT. Good. So I have these two, and I would like at the end to see whether I can get to a form like that for my penalty term. This is already, in a sense, nice, because I can already get rid of theta country and theta city, express both of them as a function of gamma ct. But I would like to get to that neater expression over there, right? Which, as you can see, you know, if you take away everything, which talks about city and country, so here should be also country, then I get just a dot product of something related to gamma city. Okay, so let us actually call in theta country, right? I can call this D, okay, and I can call the whole thing here, I can call it A, right? So that this is A times gamma ct, okay? So that this is gamma ct minus this is essentially, this is again A. So this is gamma ct minus identity minus R transposed A times gamma ct. Okay? So I have it in this form. And now I have to see the theta. So if I take now lambda over 2, the norm of theta, this is then the sum of all j's that are not city and country. So everything else of theta, where I actually add the theta country and theta city, but I add them in this form. Yeah? So now the square of the norm is exactly the dot product of the vector with itself. So this effectively means this, means I take A gamma ct with A gamma ct. And then I also add to this one here, I minus R transpose A gamma ct with I minus R transpose A gamma ct. Can you read my writing? Okay, good. So now, how can we get from this? Because ultimately what we want is to take this and translate it into that thing over there. Yeah? So let's look at this bit here. I minus R transpose A. So I minus R transpose A, right. So I minus R transpose A, right, would be this, would be I minus R transposed. A was, so I got rid of ICT, so I is ICT, okay? So to make it easier for me to write, is R transposed of times A. A was R D minus 1, okay? Yeah? Now, R transpose R from here is nothing but D minus I. Do you agree? So, this means we get I minus D minus I times D to minus 1 which is, d times d minus 1, this is identity, yeah? And I times d minus 1 is d minus 1. So we have something like I, identity minus identity, plus d2 minus 1, which is d2 minus 1. Okay? So this is one part. So now, effectively, this means this, that if I look at this bit, which I want, in fact, to expand, because the rest is irrelevant to us, I have the following. I have A, which is R d minus 1, gamma ct, in a dot product with R d minus 1, gamma ct, okay? Plus, now I already computed this I identity minus RTA, which turned out to be d minus 1. Yeah, so this is now d minus 1 gamma ct, d minus 1 gamma ct. And let's see what we can do here. We have d minus 1 gamma ct here. Here we have d minus 1 gamma ct, but we have also an R. So let's move R on the other side, okay, yeah, by transposing it. Yeah, we transpose it when we move it to the other side in the dot product. So this effectively means this, that we have R transpose R d minus 1 gamma ct. Now, d minus 1 gamma ct remains, which is the same as this. So we can then sum up this part with that part, right? So this is plus d minus 1 gamma ct. And now this is in a dot product with d minus 1 gamma ct. Okay? Okay? So what can we do now? We have d gamma ct here, gamma ct there. Let's actually factor it out. Yeah? If we factor it out, we get R transpose R. Let's do that as well. Yeah? And then we get, this is plus identity times d minus 1 times gamma ct. And this comes in a dot product with d minus 1 gamma ct. Now let us look at this expression. What is this expression? Identity plus R transpose R. This is D. Right? So this means I have D times D minus 1, and this becomes identity. Okay? So then what I get is I basically get gamma ct and d minus 1 gamma ct. Okay? Now this is obviously commutative, so I can, it's the same as saying d minus 1 gamma ct with gamma ct. Yeah? And what is d to minus 1? This is exactly the one we're looking for. Right? So with a couple of simplifications, we could get actually to a very nice, neat formula. Yeah? And this formula now allows us actually to think how we could possibly generalize this to more functional dependencies. Yeah? Because effectively, if you have another functional dependency of this form involving other two variables, you can then take it away from the theta and construct something of that form. Yeah? And then, if you want to retrieve back the parameters, you can always do so via the mappings. Right? Now there is actually one aspect to it, which I somehow shove under the rug so far. Namely that we now also need some linear algebra inside the database. Yeah? It's not working just with queries. In particular, we have to take inverses. To take inverses, ideally we'd like to use Cholesky decomposition, for instance. But the beauty is that these matrices may not be so large. Yeah? Because they really map domains of cities, countries, categorical domains. If the categorical domain is huge, then we may have a problem. in the sense that, scalability may actually play a role. In practice, we realize, with the kind of training data sets I showed you here, that the domains tend to be nevertheless small enough. Not as large as, the size of the query result, right? But rather something proportional to the size of the input database, obviously, right? But even smaller than that. Okay, good. So that was actually the part where it motivates that we should perhaps also look at linear algebra. And I can talk about this after the break. Thank you. Are you guys involved extracurricular with machine learning companies here? Because I heard a couple of you interested in this sort of thing. Yeah? Yeah. So is there a strong, presence? Is something like a Silicon Valley kind of hub here in Warsaw? I mean, lots of companies in this space doing software?
I don't know, it's hard to tell. I don't know. There's a lot of, so it's hard for me to say what it all means. I mean, there are at least a few that try to solve certain problems for machine learning, for like fraud detection or recommender systems.
But it's mostly targeting that is geared towards applications, right? I mean, you want to apply existing models, existing techniques to solve a particular problem.
Right. Yeah. There are companies who do actually proper R&D, like I work with one of them.
Yeah?
So, yeah.
Okay, cool. May I ask for the name of the company?
Deep Sense AI.
Deep Sense. Well, if it has deep in it, then yeah, it must be really cool. Cool. Okay. May I start? Yeah. Good. So actually, so far we went over this in-database approach, and I hope you got a sense of the potential for this. I obviously only talked about a simple model because for didactical purposes it was actually the way to go for me. But nevertheless, the same thing can apply to other models out there. It is true we don't yet know its applicability to a huge number of models simply because our time is limited. But one hope I have is that if you find this interesting, you might actually even think of on your own of how ideas along these lines could go further, right? For different models, certain models you might find very beneficial for the applications you work on. And we ended up realizing that for some of the let's say derivations we needed in the context of in-database machine learning, linear algebra plays an important role. Yeah. So then the question is, why not look at linear algebra and develop an in-database, if you like, linear algebra approach, where matrices would admit a database interpretation. That is, they would be, for instance, results of joins over databases, and we could still do, nevertheless, various linear algebra operations on them, like decomposing them, factorizing them, like taking inverses and so on, multiplying. And that's what I would like to mention to you here. Is mostly motivational, but there will be a specific twist on a classical algorithm for QR decomposition that I'm going to present to you. So the setting here is that we have input matrices defined by queries over relational databases. I will talk about the matrix A. This is the query result, where Q is the feature extraction query as we've seen before, and D is a database. We consider that A has many more rows than columns, and that's the kind of assumption here. If you want the other assumption, where you have very many columns and very few rows, then some of the ideas discussed here may be applicable there, but not all necessarily. And the idea, the underlying assumption here is that we'd like to do operations with this matrix A without having to materialize the matrix A. So why we would need linear algebra? Well, I mentioned matrix multiplication. Remember our sigma matrix, which was A transpose A, right? Or X transpose X, we had it before, right? We had to compute that. Then inversion, recall this particular formula, which we've seen when actually reparameterizing the model under functional dependencies. And an important part is matrix factorization. And I would like to talk about the QR decomposition, where you take the matrix A and decompose it into Q times R. There is also work on rank K approximation of A, where you look at so-called quadratically regularized principal component analysis and other low-rank models, right? There is a very interesting survey, in case you are interested in this, on low-rank, generalized low-rank models are called. A very nice framework that actually captures a lot of such low-rank models based on a rank K approximation of the matrix A. Effectively, the message is that in both cases, we can do something interesting. We can compute, in this case, R, and here we can compute Y, for instance, which would not depend on M, which is the size of A, the number of rows in A, which is considered to be very large. Both Y and R can be computed without actually having to materialize A, right? And I will actually focus only on this QR decomposition here, where Q is an orthogonal matrix, and this actually does depend on the size of A, but in most cases you don't really need it. Being orthogonal, sometimes it so magically disappears as it comes in a product with its inverse. And R, however, is upper triangular, and its dimension is actually n by n, where n is the number of features, right? So it's actually less than m, which is the number of samples in the training data set. So, so this matrix A is actually interesting. It appears in a number of machine learning relevant computations. For instance, for least squares problems, we just saw that if we are given A and B, a vector B, we like to find X that minimizes this particular optimization function, right? So you take A times X, and you take minus B, and you take the square of the norm. So this is least squares. This is what we've seen. So if A has linearly independent columns, then the unique solution of the least square problem is this, right? You say X is A transpose A minus 1 A transpose B. Yeah? And this A transpose A minus to minus 1 A transpose is called the Moon-Penrose pseudo-inverse. So if we can compute this sigma, right, without actually looking at A, we'll be able to compute, if we have sigma, the way we computed it before, and we use, let's say, Cholesky decomposition of it, which will take time proportional to the number of features and not to be cubic in the number of features and not in M, in the size of the query result, we actually gain something here, right? And this A transpose, if you multiply it by B, it will give you back a vector, which is again, its dimension is n, is the number of features, okay? Or the number of variables in the query, okay? So in the in-database setting, this query defines the extended input matrix. You get both A and B as part of the input. I think that this is not fair.
You'll get some too.
Okay, thank you very much. Okay, so thank you very much. So let me actually talk about Gram-Schmidt process for QR decomposition. So I'm taking Gram-Schmidt as a sort of way to illustrate how decomposition can benefit from this in-database paradigm. So, but I will explain what is this Gram-Schmidt approach, right? There is also householder reflections, and there are others, right? For Gram-Schmidt, the idea is that you get from our matrix A, here I represent it as this, we have these vectors A1 to AN, yeah? is represented by a matrix Q, E1 to En, where each vector E here would be of size, M, where M is the size of the query result. A here is also of each vector is of the size of the query result. And we get here R, which is an upper triangular matrix, which is a dot product of these E's and the A's. Okay? Usually R is what is relevant. R is n by n, where n is the number of features, whereas, as I said, Q may be large. Okay, so this is called also the thin QR decomposition of A. So what are the applications of QR? I'll just go very briefly over them to just make a sense that, if you are able to do this decomposition well, you may be able to solve other problems. So first of all, you can solve linear equations of this form, Ax equals B. What do you do? How do you do that? You decompose A using QR. Then instead of Ax equals B, you have QRx equals B. And then you essentially multiply Q transpose to the left on both sides. And because Q is orthonormal, Q transpose Q is just identity. So then this means that you get Rx equals Q transpose B. Now Q is large, but Q transpose B becomes again small, of size n, is a vector. And then R is n by n times x equals something, a vector of size n, right? So ideally, if we are able to solve Q transpose B efficiently and R efficiently, we are able to solve such a problem without having to go over M, the number of records in the query result. So then from this, we can easily, if we have Rx, we consider this Y, we can compute this, right? And then Rx equals Y, we can do it by back substitution. Why? Because R is upper triangular, right? So we start from the very bottom, we have a single equation involving a single variable, we solve it, and then we go to the next level, we have two variables, one of them being the one we just solved, and then we go up, up, up like this, and then we solve everything. There is a variant for this where we solve k sets of linear equations with the same A, and then we use the QR decomposition of A only once, right? And for all k sets, which is also great. Another one is, as I said, to compute the pseudo-inverse of a matrix with linearly independent columns. So I won't go over the details of this, but effectively the pseudo-inverse of A boils down to this, R minus 1 to Q transpose. Yeah? And perhaps more relevant application is that once you have the QR decomposition, you can do singular value decomposition, SVD. And SVD is used in a lot of settings, right? Including machine learning settings. Yeah? So, and there are standard approaches that do this that just require R, effectively, right? So the cheaper component of QR. And in least squares problems, the idea is that you may have actually A being not square, but being n by n, and then, in that case, the system is overdetermined. Okay, so let us actually look now at this Gram-Schmidt process. The idea is fairly simple, right? You look at the input A, right? We assume for the time being that we are given A, and we look at the columns in A, which are vectors, A1 to AK, small a1 to an, right? All this here. And we do a so-called projection, right, of this AK. So the definition of this projection that I will use later is this. To project the vector AK orthogonally onto the line spanned by a vector uj, you have this formula which says the projection of AK onto uj is the dot product of uj and AK over the norm of uj times uj. Yeah? So the Gram-Schmidt orthogonalization, and I will show you pictures actually taken from Wikipedia on this, and it's pretty, it's cute, I liked it, you will see. So Gram-Schmidt orthogonalization effectively does this. I construct the vectors from u1 to un, in Q as follows. U1 is A1, U2 is effectively A2, where I take the projection of A2 onto U1, so I can make them orthogonal, right? If I want to construct U3, then it's A3, where I take away from A3 its projections onto U1 and U2. So I can make U3 orthogonal to both U1 and U2. And I proceed like this until basically I construct all the vectors U. And once I have constructed the vectors U, if I actually normalize them, I get Q, my first matrix. Yeah? But that is expensive also to represent. So this is the way you do it. I will show you for 3 vectors, V1, V2, V3. And we effectively want to compute E1, E2, E3, which are basically the unit vectors of U1, U2, U3. Yeah? So effectively, I have to compute U1, U2, U3. So how can I compute it? First of all, I say that U1 is V1, okay? And then I want to compute U2. U2, I compute it from V2, where I take a projection onto U1. Yeah? And this is exactly this quantity. Then I take it away, and I get U2. Yeah? And now, I basically look at the other one. I look at V3. I take a projection onto U1. I take it away. So this is the projection, then I remove it. And then I get a V prime 3, which I also project onto U2 now. This is the quantity, the projection. And then I take it away, and then I get U3. And then I get these 3 vectors, which are orthogonal. And if I actually normalize them, I get something like this. Yeah? So that's the process. And then once we have this, once we have this, we can actually compute also the entries in R. As I will show you in a sec. But first of all, there are the following challenges. First, how can we possibly lower the complexity of Gram-Schmidt with our in-database idea? How does not materializing A help? Q has the same dimension as A. And the second thing is the Gram-Schmidt process is inherently sequential and not that parallelizable, because effectively what we do there, we compute UK based on all the previous U vectors we computed, right? So, well, we can do some things here. For the first challenge, the trick is to only use R and do not require full Q in subsequent computation. And we'll see that this is the case. And the second trick is to rewrite UK, not to refer to the previous U1 to UK minus 1, but to refer to the input A vectors. Still, there will be some, the computation is still to some extent sequential, but nevertheless, you don't have to refer to something you computed at the previous step. Everything is now referred to the input, okay? So this is the way we envisage it. So this U's we want to compute will be computed based on A's, the columns in A, yeah, the vectors in A, times some matrix which is n by n, which is cheap. Does not depend on m, its size, okay? Now, this is upper triangular, okay? And I will not go with you through the details, but you have to believe me that this is actually trivial. It's enough to say, to inline what it means U2. Oh, is A2 minus this projection on U1. Let me put instead of U1, A1, because U1 is A1. And then I rewrite the expression so that it only depends on A1 and A2. And then I do for U3, I do similarly, right? Whenever I see U2, U1 in the expression of U3, I replace them by their meaning as a function of A1, A2, right? So if you do this, you'll end up with some formula. If you stare at them a bit more, you realize that these formulas are in fact functional aggregate queries. They are FAQ expressions. And in fact, they depend on the dot products of the vectors in A. Yeah? Okay? But what are these dot products of the vectors in A? These are exactly given by our sigma matrix. Because in the sigma matrix, we looked at interactions, right, between different features and all possible features. We looked at, city with country, city with sales, and so on, city with inventory units, and so on, right? All possible combinations. Well, they were given, in fact, by the vectors. except that we don't need to really materialize these vectors. They are very sparse. They have repeating blocks. And we can compute the dot products of these vectors directly from the input. Yeah? This will be this sigma ij entries in our sigma matrix we've seen before. Yeah? So that's the whole crux of the idea. These coefficients are defined by FAQs over the entries in sigma, and we can express then Q in this form as A times C, where A is our query result, and C is this matrix I just mentioned to you, which is n by n. And C, in fact, is computed, is effectively, it can be computed efficiently. And R now, because the entries in this upper triangular matrix R are of the form EIAJ, where E would be the normalized vectors U, yeah? R is in fact expressible like this. So you have each entry in there being a dot product between vectors in C, in this new matrix we introduced, which is n by n, and products, right, of vectors from our sigma matrix. Because effectively, our sigma matrix A transpose A is A transpose with A1, A transpose to AN. And this is it. So we can compute R by virtue of, not materializing A, yeah, but instead computing dot products of the color of the vectors in A, which are given by our sigma matrix. Yeah? So computing the dot product is actually cheaper than computing each vector in the dot product. Yeah? So that's the message to take away, I would say. And if we now look at how we can use this particular QR decomposition, for instance, in case of least squares problems, if we want to compute the solution, then as we said, we've seen before, this is R2 minus 1 Q transpose B. Now, Q transpose B, if you look at what is Q transpose B, this is AC transpose B. So it is C transpose A transpose B. So it is C transpose, and then we have our dot products between the vectors in A and B, which in this case could be considered as the label, right? So it are these interactions between the features and the label. Okay? So effectively, we can also compute this here, this vector, efficiently, without actually having to materialize any of the vectors A1 to AN. Yeah? So how to compute the coefficient matrix C without A? Well, effectively, the data complexity of this is the same as for sigma, because it really depends on the dot products, right, of the vectors in A. And there are additional arguments here to make about so additional computations which only depend on the small n, that is the number of features, which I will not go over them, right? But they are in fact very, very simple. And we can parallelize and everything. So in fact, we implemented the prototype to see how this works, and we realized that, for instance, for the retailer data set I just discussed about several times so far, with the 33 numerical features and 3,702 categorical ones, sigma can be computed in 18 seconds. So this is another system with a funny name. But it's 18 seconds it takes to compute it. I already mentioned it at the very beginning of today's presentation, actually. And if you want to compute R, C, and some other vectors we need there, and linear regression on top, it will only be another 18 seconds. It's still more than if we just do it with gradient descent, because with gradient descent, for convergence, it only took us half a second on top of computing the sigma matrix. But nevertheless, we wanted to see also how long it will take us to compute the exact solution. And I'm pretty sure that a lot of this here, a lot of the computation can be further optimized. Then, interestingly, for this data set, we used LAPACK, which is the kind of state-of-the-art linear algebra library, and it couldn't compute any of this matrices and vectors, simply because it would require too much computation. It would require A to be materialized, and that would be already too large to be ingested. Yeah? And then we looked at a fragment of this data set with only 55 categorical features to see, so we basically threw away columns that would be corresponding to categorical variables. And now sigma could be computed in 6.4 seconds. These matrices we need for QR decomposition only in 1 second. And R now, the matrix R can be computed by LAPACK in 313 seconds on one core. But it will also need to read also the data in, which will be 70 seconds. And on all 8 cores, its performance is about 7 times better. So LAPACK can indeed, parallelize well all these matrix computations, right? Except that it still has the lag of, the trouble of having to ingest so much data and working on very large data sets. And so that is the, yeah.
So by computation by LAPACK, you mean taking the denormalized data and one-hot encoding on the category?
Yes. So yeah, you have to somehow to translate the data, all data into a numerical format, and that is we use the one-hot encoding here.
Do you recall what was the average number of categories for each of the categorical features? Or what is? Are we talking about like 10 or?
No. So when I say here 55 categorical features, I mean the number of all categories. Yeah, the number of all categories. So here 3,702 would mean the number of all categories we have there.
Basically, number of columns after one column.
Yeah, exactly. So this means effectively that if you look at the matrix given as input, has something like 88 columns, and the number of rows would be 84 million something. Yeah, but that's a good question. Okay, so I wanted to give you this. No, so this is still something to investigate a lot, right? It's not the end of the game. And although I worked also on low rank approximation, matrix approximation, I'm not going to talk here about. And that's about it. We have well, there is something to go beyond. For instance. We did things like polynomial regression, if you want, the papers describe this in detail, factorization machines. The most difficult part, which requires really a lot of mathematical thinking, is how to reparameterize the models under functional dependencies, because it turns out that depending on the model, the formulas I showed you may be different, right? So, and this is where, people like you may be actually at home, and you can actually make a lot of contribution. We did the decision trees, classification regression trees, that is the principal component analysis. We are now, as I said, looking at these low rank models. A very interesting deep model, is sumproduct networks. I don't know if you heard of this. This comes mostly from the statistical relational AI community. The idea is that you have a hierarchical way of representing a probability distribution that actually you learn from the data. Yeah, probability joint distribution you learn from the data. But it's in a very, very hierarchical way and can have very many levels, making it deep. And you can do lots of things with it. You can do classification, you can do regression, and so on. And we think it's actually quite interesting also because it allows for explanations. It allows for tractable inference and other goodies. Now we looked also at unsupervised learning, such as, we looked at k-means, at k-median clustering, and there is a lot of interesting stuff that can be done on that in that space. In fact, gradient boosting decision trees I just mentioned to you, right? This is now what my nights are about, and random forests. Random forests can be done very easily for us immediately out of the decision trees. But the most important aspect to take away here is that in all these cases, you can take the model or the task you have to do, learn that model, and you can translate it into a bunch of aggregates which you can then compute efficiently. So in this sense, the kind of work I showed you before on, hypertext decompositions, on variable orders, on all these width measures, they actually are relevant. So that is the main takeaway I would like to say of this mini course. Yeah, they can be very relevant. They do require some investigation. They are not really easy to get for the wide audience because it does require a certain background to understand them. But they may be competitive. If you think in terms of your solution versus other solutions requiring to materialize the input. You don't require to materialize the input. You may gain a lot because data is sparse. Yeah? And that is the message, right? There are models for which we cannot really do very well, like logistic regression, but we can think of approximating logistic regression by other means. One thing, for instance, we basically try to look at loss functions which are convex, ideally differentiable. If not, they should allow subgradients. So one line of work, for instance, which we are going to publish very recently, is on using hinge loss. And then you can do SVM, you can do ReLU, right? These rectifiers, right? Used in neural nets. And here, if you look at the loss function, right? It is a maximum of 0 and something which depends on the data. This does not allow, would not admit gradients, but it does admit subgradient, on the portion where 1 minus y times the dot product of theta in x would be less than 0. Okay. So this means that this requires another type of computation. We have to do aggregates, but now in the presence of some inequalities. Because not all samples from the training data set will satisfy the inequality. And you only want to learn over those samples that satisfy the inequality. Now, solving inequalities is essentially boiling down to computing inequality joints in databases. So there again, we go back to databases. Can we do that faster? Can we derive the variable orders, hypertext decompositions, the weeds we discussed, now in the context of inequality joints, right? So this is actually a very fascinating question, also for your exam, in case you fancy. But there are other types of loss functions that go beyond polynomial loss, like Huber, interval, and so on. Yes?
It's not very obvious for me. Why logistic regression is hard for this?
So logistic regression, this is a good question. Why is logistic regression hard? If you look at the form of the function, it has an exponent in it, yeah? And this exponent, it has e to the power of something which is the dot product of theta in x and something else, like minus, plus, whatever, right? So what actually happens there is that we cannot actually factor out, decouple the computation over theta, over the parameters, from the computation over the features. You see what I'm saying? Because, it forces you to go sample by sample and compute that dot product. But what I would like is to push the summation over the samples inside this exponent. So I can sample over the features and separately will be the thetas. And that is the reason, right? But, there are approximations to this, right? And, people take various types of approximations anyway to logistic regression.
What about the log loss? So your examples were for the square loss, right?
Yeah.
And if you do the log loss, the logarithm loss, this is also problematic, right? Or not?
Well, okay, ultimately, if you do this loss, again, can you decouple thetas from x? If you don't, and I think you cannot in log loss, you say, I think it might not work out immediately. Yeah, and that's the thing. Okay, some references, and here is a quiz which I meant for you to take home. So the idea, what I want you is to exercise exactly this, the ideas, the concepts presented in the lecture today. Namely, if I give you a data set, a database, and I tell you, oh, this is the feature extraction query, can you write down the aggregates you have to compute? Can you think of ways to, optimize these aggregates? Because what happens with these aggregates is that because they are over the same join, you may actually break them down into little pieces, and you may share these little pieces across them, so that you don't have to compute each aggregate individually. You see? You may be able to reuse computation across them. And that is the thing. And I guess some of them, of you will have to take an exam, and I would like this to be perhaps part of an exam, right? To look at such aggregates, to look at, to design, to explain what would be the widths to compute them, how to compute them, and whether you can go beyond and perhaps even share some computation across them. Yeah? Questions? I can go over some of the things if you like. There are also quizzes I gave 2 days ago and 1 day ago, and if you have any questions about any of those, I would be happy to take questions. So one thing, for instance, in this on functional dependencies, what I would like you to, for instance, think about is what happens if you have city involved in several functional dependencies. Yeah? Or what happens if you have a composite functional dependency where you have 2 variables implying another variable, right? How would you deal with that? Following the kind of, in the spirit of what we did, could you go beyond that? I'm telling you something. In the real data sets I've seen, right, and thanks to my collaboration with the industry, data sets tend to have a lot of functional dependencies, right? This is a fact of life. And they tend to have a lot of categorical features, where if you have a feature or not, it can make a big impact, as you noticed in case for your question, right? With this laypack, once you do the one-hot encoding, and you have many categories, it can blow up the whole thing, right? It doesn't really blow it up, let's say, asymptotically, but because of this, very, very wide, arrays, somehow for some reason it cannot work. A problem I realized also with the one-hot encoding is that tools that are designed to be integrated with databases, like there is one called MadLib, right, where they say, we compute the data inside the database, but we now add various functionality, such as, for regression models, for classification, whatever, as user-defined aggregate functions implemented inside the database. Yeah? So they are actually restricted a lot by what Postgres assumes to be a decent table. And Postgres, for instance, assumes that you should not have tables with more than 1066 columns. So if you do one-hot encoding, bang, it says, I'm sorry, I cannot store this data. Yeah? So this is why there is a lot of work to be done at this interface between systems managing data and systems taking advantage of that, for building sophisticated models. Yeah? So would you guys be okay with questions on functional dependencies and looking at writing down FAQs for functional aggregate queries, right, to express models and how to analyze their complexity, and yeah, should be okay, no? So that would be the kind of questions, because if you think about it, this is where we went with the whole course, right? Yeah. So that would test your understanding of how of a bit of linear algebra and how you can use it for functional dependencies, for specific models, and also of FAQs, of widths, of hypertext decompositions, or variable orders. Yeah? So essentially everything we did in the course. Okay, then, if there are no questions, I should stop talking. Yeah?
Question, could you add more data to this? to this linear algebra? Like another rows, another columns.
Sorry, another what?
Can you add another more data to this? So when you process it, and then you add a row or you add a column.
So you want to have public.
Yeah. You have to. Yeah. This is a very good question. You know, because of time limitation, I wasn't able to really show you a more general solution towards maintaining functional aggregate queries under data updates. But there is work on that with nice complexities and everything, right? So yes, you can. The answer is yes, you can. It can be very neat, very elegant. It uses this ring formalism, right? And you can design specific rings for specific applications, in fact, right? Which makes it even more interesting. But I wasn't in the position to talk about it here. But you are right. This is a very important subject. Imagine you would like to you compute a model and you want to refresh it. You don't want to recompute it from scratch. You just want to refresh the model. With our approach here, I mean, to give you some numbers from the top of my head for this retailer data set, because we use this as a workhorse for a lot of things, so we have a common basis to discuss, you know, relative performance. We developed a system that can maintain models like this linear regression models, with about 10 million inserts or deletes per second, right, to get an impression. And this is actually on one core, on one machine. All right, so it can be very, very fast. By using a bit the mechanism I just described for this data update problem, right, with counting triangles. Computing views, maintaining the views, and using views following a certain variable order in general, right? So the whole subject of hypertext decomposition, variable orders, plays there a role as well, right? So it can be very interesting. An additional problem I could set for the exam would be for you to investigate, you know, a worst-case optimal result for another query, not only the triangle query, you know, under data updates. So that could be also something very interesting, which is doable. You know, if you sit down and you really understood the topic, you will be able to do it as well. So I can make it as an optional thing. No, you can choose either one or the other. Yeah, could be. I mean, how much time do you guys have to do such a thing, such an exam?
I'll tell you that.
Okay. No, but because you know, at least at Oxford there is an official time. They are expected to finish in that time, but they never finish in that time. They always take 3-4 times more, you know, for all these take-home exams. Because you know, if you get into it, you will then want to do it better and better. Okay, good. Thank you, guys.